Okay. Okay, so we started the last day. We will tell about the tectonic of the Himalaya with a brief overview with the main tectonic unit with a focus on the metamorphic core. And then we'll speak about the main fault and shear zones, such as the main central thrust, so Tibetan detachment, and the higher Himalayan discontinuity with the kinematics and timing. And we will apply some of the things that we learned on the days before. Okay, so we started to see what is the general architecture of the Himalayan belt. The Himalaya is very famous, it's the most famous collisional belt in the world. Most people study it, and the Himalaya provides a good look to a continent-continent collision. It is the world's youngest and highest mountain range. There is the fastest uplift rate up to 10 millimeters for year in the Nanga Parbat, in the northwestern part of the belt. There is the world's maximum relative relief. There is the world's largest high plateau, the Tibet, more or less 5,000 kilometers, and it is produced from almost an orthogonal collision between India and Asia. As a morphology, you know very well, the length is 2,500 kilometers, and we have the two corners of the indentation that are the Nanga Parbat on the northwest and the Nacha Barwa to the northeast. And actually, the convergence rate by GPS is nearly 5 millimeter per year. And so you have active faults, as Mahesh showed very nice yesterday. You can see here a picture showing earthquakes and velocity of deformation by GPS. And this picture is from a book, Himalaya Dynamic of the Giant, edited by Epard and Catin, two French geologists. There are three books with this collection, and it is written especially for master and PhD students. I sent the PDF to Mahesh. There are several topics and could be useful for you to go into depth of the geology of this beautiful mountain range. Okay, just to recall the history, there is a fragmentation of Pangaea supercontinent. As you can see, India moved for maybe all over the world from south to north up to collide with the Asia continent. There is also a northern part that is now included in the belt, that is called Greater India, is one that is now no more present in the continent, but involved in the deformation of the belt. And during the subduction of the Chinese lithosphere, the rate of convergence was very fast, up to 16 centimeters per year. And an Andean type margin developed in the Lhasa block, characterized by trans-Himalayan calc-alkaline batholith with vulcanites. And after collision, the rate of convergence decreases at more or less 4 or 5 centimeters per year, close to the collision time, maybe 60, 55 million years. Is just a look from an old picture from a French geologist, Allegre, that show more or less the development of the belt. You have also southern Tibet here, northern India here, and a lot of convergence, subduction, collision between southern Tibet and northern Tibet, the Mangong Nuyang Sushar. Then the subduction of the lithosphere below Tibet, magmatic arc, calc-alkaline arc, more or less in this part. Then collision, the development of a Hindu-Sushar zone, and then the formation of the main thrust, such as the main central thrust, main boundary thrust, main frontal thrust. They is just not very well constrained because the paper is quite old, but just to have an idea what happened it is a nice scheme. Okay, Himalayan belt is also famous for the indentation tectonics developed by Paul Tapponier in the 70s. He made several analog experiments with plasticine and the wood, and he more or less was able to reproduce the main fault to the movement of India to the north, indentating into Asia. So this is a picture you can see the main fault, the extrusion of China to the east and South China to the southwest. And this was a picture of one of the first experiment made by Paul Saponier. This is one of the original picture of these experiments that linked to these experiments. And here, also in this picture from Himalaya Dynamic of a Giant, you can see the aerial photo of Tibet and Himalaya, and here by Taponier and Molnar 1976, the slip line model with a prediction of the geometry of the strike slip fault. This is a model, more or less, a very simple model, and you can see the real strike slip fault linked to the indentation. It was a nice discovery, then also exported in another part of the world. So now we give a look to the geometry and architecture of the belt. Here you can see the main rocks, the main tectonic units. In red, you can see the Indo-Social zone. In dark red, the Ganges batholith, the Andean type arc during the subduction of the oceanic lithosphere. In yellow-orange, there is a Tethyan sedimentary sequence, the more or less a sedimentary sequence with very low or no grade of metamorphism, with the deformation top to the south with the folds, reverse defaults, and so on. In the middle part, you can see a lot of this red stuff that are north Himalayan granite or gneiss dome that has the same rocks as in the Greater Himalayan sequence, that is the violet color here. The yellow line is more or less the trace or the main trace of the South Tibetan detachment, separating the Tethyan rocks from the lower Greater Himalayan sequence. Here you can see close to the detachment, this red stuff are leucogranites, Miocene leucogranites just emplaced below or within the South Tibetan detachment here. Then in green, the Lesser Himalayan sequence, and in green also the main central thrust with several window in this part, sun clip, the other part, then the main boundary thrust and main frontal thrust, and then your country just here. This is a nice picture from a Swiss geologist in the 90s, made a nice PhD thesis in Zanskar, and this a cross section, you can see the suture, the batholith of Ladakh, the Theta Himalayan sequence, and there is also here the Tsomorari Nap with eclogites intruded in the Puga gneisses, and the Nap crystalline is a Greater Himalayan sequence. With the Zangska shear zone is a strand of the South Tibetan detachment with a top down to the north normal sense of shear associated with the intrusion of leucogranites. Then the main central thrust, the main boundary thrust, the less Himalaya here, with some antiformal shape in the frontal part of the belt. This is a picture built up by Max Searle at the altitude of Kathmandu, central Nepal. More or less the same things. There is no the Tsomorari Nap in this part of the belt. But what you can see, a large amount of leucogranites and granite seal just in the upper part of the Greater Himalayan sequence and close to the South Tibetan detachment. Some leucogranites are really deformed and sheared by the movement of the Greater Himalayan sequence. You can also observe some isograde of minerals, sillimanite, kyanite, sterolite. So approaching to the main central thrust, there is an inverse metamorphic gradient due to several factors, maybe deformation, sure. You can see also the external clip of the grid Hermannien sequence. Sometimes in this clip are some rocks of the Tethyan sediments. So more or less the same. You can see here also the Gorka earthquake rupture zone. The Gorka earthquake was caused by this step geometry of the main frontal thrust just below the belt, because in this part strain accumulated for 100 years and then was released during the 2015 earthquake. Okay, this is just another view of the same thing by Rick Lowe. You can see more or less also the topography here, and the units are exactly the same. This red line is more or less the brittle zone where earthquakes generates, because we are in the upper brittle part of the crust with brittle way of deformation. Below there is a creeping zone in pressure and temperature increase, so deformation is low and continuous, so with no development of earthquakes. Okay, we started to give a look to the Theta Himalayan sequence or Tibetan sedimentary sequence, a different name of the same unit. You can see here, this is a road from the road to Le, from okay, from the I don't remember the name, Mana, from Mana to Le. And during the road, you can see these beautiful folds. The sediments are really deformed in very large folds continuously. And so by this kind of fold, you can calculate the shortening that is has been estimated to 700, 1,000 kilometers. Just 150, 300 kilometers have been documented in the folded and trusted sediments of the Titan sedimentary sequence. This is a total shortening, sorry. And the minimum of 650 kilometers of shortening have been detected in the Lesser Himalaya. And whereas in the Greater Himalayan sequence, because you have a lot of metamorphic rocks, so the folds are much more complex. So there is metamorphism, superposed fold. It is not possible to calculate the shortening, but sure is higher than the shortening recorded in the upper Titan sediments and in the lower less Himalayan sediments. Just a look to the rocks. Here you can see some Triassic limestone, some Ordovician limestone. This is a drill for paleomagnetic studies. These are in Appel, a German geologist working on paleomagnetism of the Himalaya. It's quite famous. And in this very simplified geological section, you can see the lower part of the Greater Himalayan sequence, the South Tibetan detachment, then the Tibetan rocks with limestone, and at the base of the limestone are strongly foliated and with a little bit metamorphism. Then you have orange limestone is shale at Devonian time, Silurian Devonian, Carboniferous and Permian sandstone and siltstone, but more or less what we can observe is usually an increase in deformation and in temperature approaching the Greater Himalayan sequence, because here you have leucogranite injection complex made by dikes and silts and migmatites. So you have very hot rocks below the Tethyan rocks, so there is a transfer of heat from below to the upper part. So this, at least the base for 800 meters, 1 kilometer, so the base is a little bit metamorphosed by dynamic metamorphism, because the heat transfer happened during the shearing of the South Tibetan detachment. And probably, since there are this kind of faults, very, very common, reported in the Tethyan Himalayan sequence like this. We are more or less close to Lhasa, of the Lhasa from or the road from Lhasa to Mount Everest in the Tibetan side. There are a lot of South Virgin Falls and thrust with top to the southwest and south shear. So probably the Tethyan sequence was firstly trusted on the Greater Himalayan sequence and then affected by shearing, normal shearing at the base. Sometimes people forgot this, especially in calculating the amount of displacement of South Tibetan detachment, because the superposition is not only due to the normal shearing, but first thrust and then shearing. So it's tricky. It's difficult to calculate the uh, amount of displacement. Going down, we are in the higher Himalayan crystalline, that is a metamorphic core of the belt. Has been classically differentiated in three formations by Patrick Lefort in the 70s, but of course they are not formation because we are not in a sedimentary sequence, but there are at least a unit or complex. So the upper one, the unit 3, is just this one in this part, is made by orthognesis and migmatite gneisses. You can see here a picture in Western Nepal with large feldspar porphyroclast, and below a picture from Western Bhutan. You can see the white stuff are crystal of sillimanite, very huge crystal, and the red dots are garnets. So is a garnet and sillimanite bearing gneisses from the upper part. So we are just in this unit, the pink unit, below the Tethyan rocks and above the main central thrust. Okay. So other picture from the Greater Mayan sequence. This is from Mount Makalu. You can see strongly sheared gneisses with very big garnet crystal, testifying high grade or medium grade metamorphism. It's a similar orthogneiss to the previous picture. They are very common, and when dated, there are of Ordovician age, these orthogneisses. Okay, the Greater Mayan sequence is made also by a lot of white marble, calc-silicate gneisses, with minor amount of pelitic and psamitic rocks. You can see here a Boudin of calc-silicate in Western Bhutan, in Western Nepal, and here a thin section of a marble, where you can see the calcite crystal, obviously deformed with grain boundary migration or twins like this. So you can study the microstructure of this rock very easily. Going down in the unit 1, there are more or less kyanite and garnet bearing paragneiss and mica schist. You can see kyanite in the field here in western Nepal, kyanite in Kaligandaki Valley, and the kyanite in thin section like this. This, this mineral is kyanite in quartz matrix. There are also some, of course, calcosilicate and Boudin of garnet bearing amphibolites. This basic composition. So we are at the base of the Greater Himalayan sequence, called also Higher Himalayan crystalline, but in the last few years, Greater Himalayan sequence is the most common used name. In this picture, you can see some other rocks, garnet, kyanite, sterolite, migmatite rocks at the mesoscale. At the microscale, you can see sterolite with internal foliation, garnet, sorry, sterolite here, kyanite, white mica, biotite, quartz, and here you can see a beautiful garnet with an internal foliation truncated by the external foliation. This is from the chapter of the book Himalaya Dynamic of Giant, where me and colleague Centurion described the tectonic and metamorphic feature of the Greater Himalayan sequence, just an abstract but is useful. Of course, in the greater Mayan sequence, in the upper part, there are a lot of migmatites. Mm, Maybe half part of the greater Mayan sequence is made of melted rocks. You can see here melt this stuff, leucosome, concentrated along a shear band at the outcrop scale. And this sigma type porphyroclast in migmatite linked to the top to the south shearing. That is the main deformation affecting the metamorphic rocks in the sequence. Sometimes you can observe folds in the migmatites, and leucosome try to concentrate along the axial plane of the folds. Here you can see also some sheared leucogranite dike, because migmatite are associated with granite and leucogranite, and probably they are the origin of the leucogranite. And you can see the sigma type shape with the top to the southeast sense of shear. Oh, this is an old picture from Nialam in southern Tibet, just at the boundary between Nepal and Tibet. This is gneiss with some dikes of leucogranite. This a piece of leucogranite intruded in these high-grade rocks. And this is a tourmaline bearing leucogranite in Gangotri, in India. There are, of course, a lot of granite in the upper part. It's just an aerial a picture from the flight from Kathmandu to Bhutan. This is Mount Everest, Mount Lotz. Here you can see this white stuff is a big intrusion of granite. The thickness is 4 or 5 kilometers. Here you can see a big leucogranite seal in Bhagirati. Is more or less Tethyan rocks, Greater Mayan sequence, and in between there is a big seal. This is a horizontal attitude of this seal. Okay, this is Bhagirati Massive, our camp some years ago, and a lot of rocks and a lot of moraines, more or less. So it is a picture of the Mount Makalu. The Mount Makalu is made at the top by leucogranites. You can see the dark stuff below. There are migmatites, and if you give a close look, you can see that there are a lot of dike and seal from the migmatite, and they increase in volume towards the upper part until they build up the main granite of the Makalu massive mountain. Okay, this kind of leucogranite are highly differentiated granite with paraluminous composition, sometimes with garnet, white mica, and so on. But they are now considered for the formation of lithium and rare earth element because of the rapid crystallization and shearing. So the shearing is very important to generate lithium-rich pegmatites. This is a picture from this very recent paper, just published a few days ago. Here, Rambuk Monastery, the Mount Everest, Chomolagma is the Chinese name, and these red stuff are all the granites. This is Choyo Mountain with Pusila granite. So there is a road here coming from Tibet to Nepal. So it is quite easy to reach this kind of granite. This no, this is too much high. But there are a lot of granite with possible interest for rare earth elements and lithium that is now very important for energy transition. Okay, there is a nice intrusion in Western Nepal that we found several years ago. This is a granite never found before that we named the Buraburi. It is a double peak, means sister and brother, more or less, Nepalese, if I remember well. The very important feature of this granite that is included both the Greater Mayan sequence in in pink and Tibetan sedimentary rocks in light brown. So it is one of the few granites including the South Tibetan detachment. As you can see in this picture, the granite is isotropic, has no deformation, so you can put a limit on the deformation of the activity of South Tibetan detachment. This is a picture showing the granite in the lower part, this kind of rocks. These other rocks are sedimentary rocks of the Titan Himalayan sequence. This is a pass that we are not able to cross because on the other side there was a lot of ice, so we come back. So we made several expeditions from southern part, from northern part, just to map the granite, and at the end we mapped by aerial photos and um, other kind uh, of similar things because of course there is no coverage of vegetation because we are more or less at 5,000 meters of altitude, so the rocks are very well exposed, so it was very easy to map. The area of this granite is 110 kilometers square, and the thickness is more or less 5 kilometers from the base to the top. And it was never mapped or before our expedition because it is a very far region, not used by tourists. So paradise for geologists, more or less. Okay, just a few pictures from the Lesser Himalayan sequence. So if we go down from the Greater Himalayan sequence, we found the Lesser Himalayan sequence, ripple marks here in Western Nepal, and some cross bedding in quartzite in this picture. Okay, just an overview of this tectonic unit. If we give a look to the metamorphism of Lesser Himalaya, main central thrust zone, Greater Himalayan sequence, people detected a difference in the PT path because in Greater Himalayan sequence there is a PT path like this, pressure and temperature, increasing pressure and temperature, peak, then exhumation, decreasing temperature, decreasing pressure more or less at the same temperature, then decreasing both during the final stages of exhumation. Greater Himalayan sequence reach pressure of maybe 1.6, 1.8 gigapascal. The main central thrust zone, the boundary between the upper main central thrust and the lower, show a PT path like this, more or less. So a little bit different with lower pressure with respect to the Greater Himalayan sequence. And the lesser Himalayan rocks, when involved in the belt, show the so-called Alpine PT path. So very different shape, this one. So they go quickly to pressure, but no high pressure, then come back to exhumation. Because lesser Himalayan sequence is more or less confined in the upper class. The pressure are no higher than 5 kilobars. And you can see here more or less the provenance of this PT path. The blue came from this Greater Himalayan sequence, the yellow-orange from the main central thrust zone, and the green from the lesser Himalayan sequence in this way. Okay, now we give a look to the main fault and shear zone. Is the South Tibetan detachment, the high Himalayan discontinuity, and the main central thrust. In this picture from a paper of Garzanti 2019, we can see a section of the Greater Himalayan sequence. Here, the South Tibetan detachment at the top of the metamorphic sequence. In the middle part, the high Himalayan thrust or higher Himalayan discontinuity, the main central thrust zone, the main boundary thrust, and so on. Here you can see in this schematic cross-section, South Tibetan detachment, the high Himalayan discontinuity, main central thrust, and this is an out-of-sequence thrust, this red line, this dot red line. Okay, there are more or less also the ages of this shear zone, 25 up to 11 million years South Tibetan detachment, high Germanic discontinuity between 27, 28 and 16, 17 million years, main central thrust less than 16 million years, then boundary thrust younger than 10 million years. You can see also that in this picture, the upper Greater Himalaya is found also in the North Himalayan gneiss dome. There's a Titan sediments here and here. In the middle part, you can find this alignment, east-west alignment of gneiss dome, North Himalayan gneiss dome, and they are made exactly by the same rocks and the same leucogranites that we found in the frontal part of the belt. One of the main features of this uh, shear zone is spectacular continuity all along the belt, because the same feature you can observe in Bhutan, Nepal, India, in several sections, more or less they have the same characteristics. So it's very uncommon because, for example, if you study the Alps, the tectonic boundary are different characteristics. It is not so linear, the orogen, and is much more complex. In this way, at least from this point of view, we are facilitated because of this beautiful continuity of the shear zone. Okay. For the STDS, the direction of tectonic movement is towards the northeast, and the displacement is about 100 kilometers calculated along the Mount Everest section. And the blue line marks the South Tibetan detachment. The lower thrust fault, the main central thrust, has a top to the southwest contractional sense of shear, so it is like thrust, of course. The displacement is more than 200 kilometers. Okay, if you give a look to the arrow, you you have more or less in the Greater sequence an arrow. Oh, sorry, this an arrow like this, an arrow like this. If they sum up, they make show a big arrow pointing to the extrusion, a movement to the upper part and to the south of the Greater Himalayan sequence. Uh, in this way, is a STDS, MCT. The movement is like this, of course, is a normal sense of shear. So if you sum up this vector, you have a big one with a south-southwest. So means that these kind of rocks in the greater Himalayan sequence are extruded, are pushed towards the south by the kinematic of this fault. Because you move this part down and this part up. So just as a consequence of the kinematic of this two bounding fault shear zone, there is a movement to the upper part. Here uh, we are in the Kaligandaki Valley, this Mount Dhaulagiri, that is now 8,000. And from the footpath to Annapurna Base Camp, there is a place where there is a nice view where you can see more or less the trace of the main central truss and the trace of the Annapurna detachment here, that is a strand of the South Tibetan detachment. And all this stuff is the Greater Himalayan sequence. Mm. Is, of course, a panoramic view, a little bit contracted. In these mountains, the Lesser Himalayan sequence, and you can see here this part. This part is made by the foliation deep into the north and some fracture deep into the south, and they made a big collapse of slope coming down and building up hills up to 500, 600 meters of altitude in the Kaligandaki Valley. There may be this one, the bigger. So uh, also this kind of foliation sitting deep into the north. So at least at the first sight it could be stable, but if cut by joints or faults deep into the south, they can cause a wedge failure of the rock. And this is one of the biggest I have been seen in my life. So, okay, this section are from George Gruitz and Isabel Cotan from the Himalayan Dynamic of a Giant, showing more or less two cross section, one from Bhutan, more or less. Yeah, you can see main central thrust a little bit folded down, the South Tibetan detachment, the Kangmar Dome here, or organized dome, and here a section from Mount Everest, where we can see made by all the paper, one of my first paper in the Himalayas, 1998, and Serle 2003, where we can see Mount Everest here is Tibet. The Mount Everest is cross-cut by Chomolungma detachment, that is a brittle fault with the top down to the north sense of shear, and the Lhotse detachment here below. This is a ductile shear zone. This is a brittle shear zone. So in this, in several parts of the belt, the South Tibetan detachment is not only made by one shear zone, but you have a lower ductile shear zone and an upper brittle shear zone. But in not every place it is the same. Then there are some normal fault like this, high angle normal fault cross-cutting the detachment. And in this way, you can see this brown stuff that is a Norcol formation, so-called Norcol formation made by low-grade metamorphic rocks or up to medium grade that show a thickness of a few thousand meters here. But since this fault merged to the north we can observe these low-grade non-metamorphosed metamorphic rocks that occupy the top of Mount Everest directly on top of the high-grade metamorphic rocks. I will show you some picture later. Okay, now we give a detailed look to the main central thrust. The main central thrust is this line in between orange and green the unit with some tectonic window and some clip. So, okay. There is a problem of definition of the main central thrust because it is one of the main tectonic feature of the Himalayan belt, but there are several definitions, so it is a mess when you can go to see the map, and people put the main central thrust in very different ways. So classically, main central thrust have been defined as a boundary between higher Himalayan crystalline or greater Himalayan sequence and the lower, lesser Himalayan sequence. This was a definition by Haim and Ganser, 1939, and therefore located at the lithological contact and partly metamorphic variation. Other authors, such as the French colleagues, especially some years ago, Lefort, Colchen, put the main central thrust at the kyanite in isograde. When kyanite started to grow in the rocks, they put the main central thrust. So it is interpreted as essentially as a metamorphic boundary. Some authors point to the occurrence of a zone of high-grade Eiger deformation, such as Searle and others 2018. There is a nice paper on Geological Society of London, just a review paper with some suggestions. I suggest you to give a look to this paper. So they say if it is a shared zone, it should be characterized by high strain. This is, of course, it is correct. The main problem is that sometimes the formation is heterogeneously distributed. So you have sometimes you find with several zones of high deformation. So it is not really easy also to follow this very clear uh, criteria. More or less, the main central truss, it is not a single truss surface, but there are at least two main surfaces, an upper main central truss, a lower main central truss that Arita, um, Japanese colleagues, called the main CT1 and main MCT2, uh, or it is an extensive zone of deformation that we call the main central truss zone, because if you go from the higher truss to the lower truss, you found maybe kilometers of mylonites with no solution of continuity. This is a summary of the criteria used to define the main central truss. The first one is the structural criteria. So you have high-grade ignesis and migmatites in the upper part with a ductile shear zone in between the upper and the lower unit. In the below, you have low-grade metasediments, the lesser Himalayan sequence. The main interpretation is major thrust, so up to the southwest movement, and shear zone with mylonite. So very high strain shear zone. This could be the most classical definition, the most useful. There is also metamorphic criteria. You have amphibolite facies metamorphism with silmanite rocks above, a green schist facies to the south below. So there is a metamorphic discontinuity with inverted, sorry, there is an error here, inverted metamorphic sequence. There is a lithological criteria, aragnite, migmatite, and leucogranite above, phyllite, quartzite, and carbonate rocks below. So there is a lithological contrast. There is also a geochemical criteria, epsilon neodymium, because if you give a look to the rocks from the grit element sequence or from the lesser element sequence, epsilon neodymium point to younger sources in the grit element sequence. So this value is from 15 to 10, and epsilon neodymium in below the main central truss in the lesser Himalayan sequence point to 25 to 20, pointing to the very much more older source from the Indian Creton. So there is also an isotopic boundary. Some people use also the trital zircons to gain the age of sedimentation of the rocks. And also in this case, you have concentration of ages from 1.2 to 0.5 gigahertz, a little bit young with respect to the lesser Himalayan sequence below. It is 2.1, 1.8 gigahertz, much more older. So it is based by different sediments provenance. It is more or less confirmed by several authors. But the main problem is that, for example, in central Nepal, the main central truss has been put by Max Serre, for example, in the lesser Himalayan sequence, maybe 30 kilometers away from the main central truss marked by French geologists, so in the lesser Himalayan sequence, when the formation disappear. And some people, for example, put the main central thrust up to the migmatite in the upper part of Greater Himalayan sequence. In in Sikkim, Himalaya, there are map with the main central thrust in the migmatites. So there is a very strong difference in distance and the kind of rocks involved um, in this problem. So sometimes it is not easy to compare map from different parts of the belt. There are some picture for the main central thrust zone. The picture are from George Gruitz, for the most part, apart the two in section from Salvatore Carino and Chiara Montomoli. Here you can see a sharp contact in the picture A, SC fabric or SC prime fabric here in fill lights is a very common aspect of the main central thrust in the field. Also, you can see here some orthogneisis involved in the deformation. So in this case, you have uh, sigma sigma type porphyroclast OSC structure. You can see uh, very penetrative foliation in this orthognesis, and usually when you are away from the main central thrust, the deformation is not so strong. So also the gradient of deformation suggests the occurrence of the shear zone and also kinematic indicators. Here you can see some SC fabric, not well observable in this picture. We stop to the south. There are some rotated garnet in the main central thrust zone. This picture from Salvatore Iaccarino from Turin, or some mica fish like this. This photo is by Chiara Montomoli, maybe from Western Nepal. So very large mica fish, suggesting a top to the southwest sense of shear. So about the sense of shear, there are no problem, both at the mesoscale and at the micro scale. This is a picture of main central truss with SC fabric with a very large distance. This is a lens cap, and you can see the distance between C plane here, maybe 20 centimeters, so very, very huge SC fabric, or some asymmetric boudin in quartzite like this. And usually the stretching lineation, we can see a little bit here, deformed, is northeast plunging, sorry, and the SC fabric are subhorizontal. You can see the pole here. Okay, we are in Uttarakhand or Garhwal, India, with some colleagues, Salvatore Carino, Chiara Montomoli, and Dario Visona. And we are in the main central thrust. This is a rock of the Great Himalayan sequence. This is sheared rocks, and here the Lesser Himalayan sequence. Some beautiful kinematic indicators in fill lights with quartz deformed quartz vein. So you can see plane, C plane and S fabric here. There's a dextral sense of shear. In these carbonate rocks, there are foliation fish. You remember that mica fish is only one crystal. These are aggregate of mica and chlorite, so they have the shape of mica fish, but since they're aggregate, we call the foliation fish. But anyway, the sense of shear is up to the southwest. Okay. The main central thrust is famous, has been known all over the world for the inverted metamorphic sequence. You can see some cross-section from Lefort, that maybe was the first to recognize this feature in main central thrust. Is more or less in the Maka. No, okay, anyway, Eastern Nepal. You can see chlorite, biotite, garnet, staurolite. This Marziandi River. Kyanite, silimanite. So going upward, you can observe an increase in the occurrence of metamorphic minerals, increasing the metamorphism. So there are several models envisaged for the explanation of this inverted metamorphic sequence. The first one was the hot iron, because you have the Great Himalayan sequence with gneisses, migmatites put above lesser Himalayan rocks, very, very cold. So there is a transfer of heat from above to below, and this causes the growth of metamorphic minerals with decreasing temperature downward. Another explanation is localized simple shear. Hubbard, 1989, Jain and Manikaswagam, 1993. So you can have okay. Another another explanation is the folding of the isogrades. Um Localized simple shear. Okay, we can. There are picture about after. Okay, these are more or less the three main mechanism of explanation. Another one is the channel flow, because you in this picture, mainly from Mike Searle, Rick Lowe, Laurent Godin, you have molten rocks here. They are moving to the south. Now at the surface of the belt, in the frontal part, cropping out the rocks that were molten 20 million years. But with this movement, you have a hot channel with molten rocks that moving upward. So in the upper part, in the South Tibetan detachment, you have a deformation, a high strain zone. So the you have more or less a normal metamorphic sequence with the telescoped isogrades. You have sillimanite, kyanite, sterolite, garnet that approaching the shear zone are sheared and they become closer and closer each other. In the lower part, the same isograde underwent a passive deformation. So they are sheared, but you have here the sillimanite, the kyanite, sterolite, garnet. So it is not like a folding, but it is just a propagation of the heat in the frontal part with a normal sequence here, inverted here, and then sheared along the main central thrust. Because just it is the shear that make the isogrid to go very close. Okay, this is more or less mm, the model of a simple shear. You have a normal metamorphic sequence with the thrust movement and the main central thrust and a lot of simple shear equals the inversion of these isogrids, more or less. In this picture that I drew few months ago, you can see a non-deformed rocks below. Then with a large amount of simple shear, with a very large gamma value, you can rotate the lines strongly to the right. So if you put some lines, maybe 200 degrees, 300, 400, 500, 600, with a certain distance, after an angle of deformation of 25 degrees, these lines are rotated to the right, so the red distance in between the lines become shortened. With an angle of deformation of 42 degrees, the line are rotated to the right more, and this distance is decreased a lot, maybe 5 times with respect to the initial one. So in this way, by simple shear, you can explain the telescoping of this isograde that you can observe along the main central thrust as an inverted sequence and along the South Tibetan detachment as a normal one. But this happen everywhere when we have shear. Also in the Est-Variscan shear zone, if you remember, I show you that close to the Est-Variscan shear zone, we have the same increase of metamorphic Barrovian minerals. This is in the Est-Variscan shear zone. It is not due to thrust or normal fault, but to strike slip to transpressional deformation. In transpression, the telescoping is much higher because we have also a component of compression perpendicular to the boundary. So this line are flattened and put close to the other. It's very, very common. Okay, about the age of the main central thrust, the age, there are several ages with different methods, with different rocks. The main problem is what are you dating? Because if you put the main central thrust in the migmatites or in the lesser Himalaya, you are dating different things. So it is not easy to gain the ages. In this paper of several years ago, we compared the ages of the Eiger Himalayan sequence with respect to the main central thrust. The main central thrust, more or less 1713, 2510, 2513, 25:8, 16:9, 19:15. So more or less the range of age is this one. In the paper by Godin and others, 2006, and a special publication of Geological Society of London, published in 2006, a very, very nice volume. They put ages in between 25 and 16 million years. But probably not all these ages are related to the main central thrust. These are probably little bit accurate. Okay, for example, to gain good information about the age of movement, there is also this paper by Catherine Mottram in Sikkim. They used yttrium maps for garnet and monazite growing during the formation. Sorry. So this is a nice paper because it shows very well how to use garnet and monazite and at the same time with chemical mapping. So you can uh, refer to the prograde metamorphism and retrograde metamorphism happened during the main central thrust activity, and they use the yttrium content of monazite and garnet because when yttrium is sequestrated by garnet, it is depleted in the contemporaneous monazite, and the opposite happen when yttrium is released by garnet during retrometamorphism, and it is sequestrated by monazite. So monazite during the retrograde metamorphism show high yttrium rims in the crystals, like the ones that we observed in Argentera Massif and so on. Anyway, they found ages in between 17, 12 million years, and probably some deformation post 10 million years. So it was very accurate way to calculate the deformation using both microstructure, tectonics, geochemistry, and geochronology. I will show you some details of this method when we will deal about the Eiger-Malayan discontinuity. Okay. So we worked a little bit in Uttarakhand. So we collected sample from Laknanda and other valley, and of the main central trust. And during the PhD thesis of Chiara Montemagni, published in 2018, 19, and 20 in several papers. So the last one is in Terranova, about the main central trust. We detected the mica growth along shearing, some static mica above the mica growth along the formation. So we gained the ages of the main central thrust, of the Vaikrita thrust and the Munziari thrust. We are able to date the upper and the lower portion of the thrust. Here more or less the Munziari thrust here, the Vaikrita thrust here, the way to Gangotri. Here is a section with the Munziari thrust, the lower one, the Vaikrita thrust, and the Greater Himalayan sequence up to the South Tibetan detachment here, the so-called Martoli fault. Some sample were taken also in the Alaknanda and Dauliganga valleys. The Dauliganga valleys were able to reach the South Tibetan detachment close to Malari, because in Malari there is a granite that is interpreted as include both the Greater Himalayan sequence and the Tetian rocks. Some people published that it is undeformed, but in reality we were here with Arvind Jain from Roorkee University and Pulok Mukherjee from Dehradun, I think. And we found that the granite is sheared, so it is not undeformed. There are some undeformed dike, but the granite is completely sheared. Anyway, we took several samples to date the South Tibetan detachment and the main central thrust here, with, close to Tapoban, here close to Joshimat, and okay, the other part I showed you before. So this is a section Laknanda Dauliganga valleys, and we had these ages. Sin clearing mica 8.2 million years and post S2 mica 7.4 million years. The static mica, this one, this static crystal growth after the formation for the Velkita Trust. The Munziari were more or less close to 5 million years. More or less the same ages in the Velkita Trust, Laknanda Dauliganga, 9 million years. The formation stopped by static micas at 6 million years. And the Munziari Trust, more or less 5.35 million years. This was a very nice work by Igor Villa and Chiara Montemagni on argon-argon geochronology. And so we can say there is also in this picture from the paper 2020 on Terranova, we were able to also make some vorticity analysis to detect the amount of pull shear, simple shear, but not with classical method, but um, examine with X-ray the whole sample without cutting, but just showing the images. The name is oh, I now forgot, but I will come back later on this. Anyway, the Vakrita Trust was active in between 9 and 10 million years with a vorticity in between 0.75 and 0.95, point to the dominant simple shear deformation together with less amount of pure shear. After that, we had the growth of static mica along more or less at 7 million years. This means that you have the shearing at 9, 10 million years, then shearing stop. You have the growth of static mica at 7 million years, so no more deformation along this part. Then deformation migrated southward, downward to the Munzari Trust that was more or less active at 5 million years. So the upper and the lower thrust or shear zone of the main central thrust zone are not active contemporaneously, but this is older and the lower, the Munzari thrust, is younger. And at the time of activation of the Munzari thrust, deformation was characterized already by non-coaxial deformation, but with a dominant pure shear. And we can explain this because you are adding a lot of rocks to the Munzari Trust, so the lithostatic load increases, and so increases the amount of pure shear in the lower part. So younger and with a lot of load. I don't remember the name of the method. Um, okay. Okay. Can we make a minute of stop? Have you some question about this? The window, MC2. Mm. Uh, you mean to the poles? Yeah. Oh, because mm, after the formation of MCT, you have the development of duplexes in the Lesser Himalaya, and you have accumulation of duplexes, and you can make some antiformal fold. So you have some antiform and synform, and depending of the erosion, you have some clip and some window. especially in eastern Nepal. Gosa and Kund, Windove, or some similar names. I think it is they are due to the deformation in the Lesser Himalaya that passively deformed the main central thrust. Okay. Okay. You cough for tea. Within 10 minutes, we come back.